Hi, I'm Coen. Good afternoon, and I'm going to give my presentation for my master's project, which is a bit different from everyone else's, more biomedical engineering. And it's a novel approach for tumour margin assessment based on low-coherence interferometry. And I have my supervisors, Dr. Chi Fang and Dr. Brendan Kennedy, to thank. So we'll start off with our introduction to breast cancer and surgery. So first off, breast cancer is actually the second highest rate of cancer diagnosis in Australia, with about 19,000 to be predicted to be diagnosed in 2019. When someone is diagnosed with breast cancer, often you are treated with surgery. It's either mastectomy, which is complete removal of the breast, or a breast-conserving lumpectomy, where they just try and cut out the tumour. There's actually some studies to show that there's a reduced quality of life if you have a mastectomy due to the disfiguration of having a breast removed. So you think we might lean towards more breast-conserving surgery. But what we found is that there's actually a significant increase in local recurrence rate for breast-conserving surgery. About 8.8% of people who get breast-conserving surgery have local recurrence of that cancer versus the 2.3% for mastectomies. So to try and get around that, adjuvant radiotherapy is often used. Other ways of doing it is they go in for re-excisions. So about 20 to 30% of people who have lumpectomies have to go in for re-excisions later on, and that's a very expensive process. So we need to understand how surgery is done first to try and how to fix this problem. So manual palpation is actually used for breast-conserving surgery. So they'll feel around in the cavity to try and find the tumour. And there's a few problems with this. So first is the low resolution of the fingertips. You can only feel somewhere between 1 and 5 millimetres for tumour in those sort of regions. It's not objective. So some surgeons might be able to feel it and some surgeons might not. So it's quite variable depending on surgeon to surgeon. And also the amount that the surgeons decide to cut out also varies, since it becomes quite surgeon dependent or arbitrary. So we take a step back and we look at the properties of tumours and how should we go about trying to fix this. So manual palpation is based on the increased stiffness of the tumour. So you can actually feel that it's quite stiff relative to normal tissue. And we can see that on this figure here. So you can see that the breast has a Young's modulus somewhere between 10 to the 3 and 5 by 10 to the 4 pascals. And if you look at the malignant breast tumour here, there's a much larger range there. So if you find tissue that has a much higher Young's modulus around that area, it might be breast cancer. Other things that are likely to be in that cavity are calcified plaque and just adipocytes. You'll actually notice that tumour cells themselves are softer. So if you have really good resolution and you're looking at cell specific, you could maybe utilise that. Tumours have an increased density as well. So based on their high proliferation rate, they actually can stay quite small while they're reproducing. And so maybe that density could be utilised. So how are we going to utilise this to detect tumours? I'll go through a couple of different iterations of how people have tried to address this problem in the past. So tactile senses is a way to objectively try and mimic what surgeons are doing. So it's based on an array of either piezoresistive or capacitive sensors, like in your smartphone. And so they provide a stress map for the surface. So by pressing on it, you get a response that correlates with the force. The limitation with these is that you actually, they have to be sensors that are placed in an array. And so you're limited by the spatial resolution, by how far apart you can actually place them. And that's sort of 1.3 to 5 millimetres, similar to that of manual palpation. Another way of trying to fix this problem was via using an OCT. So first I'm going to just go over what an interferometer is. So it utilises laser interference to measure distance. So you have a coherent light source that goes through a beam splitter here, up to a reference mirror and back, and to the measurement mirror and back, and then they interfere, and then you have a detector at the end. And you can utilise this interference pattern to measure a distance. OCT is similar in this regard, except it uses a low coherence light source, or an oscillating mirror, or a swept light source. So lots of variations in the frequencies, meaning that you can get these sort of peaks when there's high density materials at a depth, rather than just a single distance. So it's currently used for retinal imaging, as well as some new research into skin and other properties. So our group actually proposed an optical palpation version of this, utilizing a silicon layer. So by looking at the different depths in a calibrated silicon layer, we know how it deforms. So as you put a preloaded and a loaded version onto the surface, you can see the difference in the lengths, and so you can measure a stress. This silicon layer has some titanium dioxide scatterers, so you can actually visualize it during the OCT image. It's been tested on phantoms, like in tissue mimicking phantoms with inclusions, and it's had good results, as well as with in situ tumours. The spatial resolution was about 400 micron. So this is just a couple of the images that we got from the inclusion phantom. So you can see that there was a stiff inclusion. As the layer was deformed, we could see that there was the layer deformed as well as the stiff inclusion was underneath, and we could image the square. And then for ductal carcinoma, so this was the calcification that we see in the breast, as I mentioned before, which is very stiff. The D representing the ductal carcinoma, which is an intermediate range, and then the adipocytes around it, so it's softer. So you can use that to try and delineate between tumour and not. And this is the histology to compare it with. So these are just a couple of the modalities that have been used so far. You will notice that the manual palpation, mostly used, is because it's free, except OCT image, much better resolution, very expensive. So these are the sort of things that we need to improve on. So what am I going to do about this? I suggest that we can use a cheaper version of this OCT optical palpation system based on low coherence interferometry. So if we reduce our reliance on the OCT system, it becomes a lot cheaper. We also can get rid of the depth map, because we're only looking at surface tissue, so it doesn't matter. And then we want to increase our signal to noise ratio, because by having the titanium dioxide scatterers, we can it becomes a much noisier signal. So typically, an OCT light source has a bandwidth of about 20 terahertz with a coherence length of about 5 micron. And that 5 micron is the distance between these various peaks that we could possibly pick up. And so that's our limit for our depth measurements. In the OCT approach, we're actually detecting both sides. So we're looking at the actual contraction of the layer. By using a simpler light source with a longer coherence length, we can just look at the relative position on our coherence function rather than looking at peaks between them. So as you can see here, so this is, if we use a longer coherence length rather than the short peaks, we can just look at, we've just gone a little bit, but based on our theoretical coherence function, this is what it looks like. And this is how far we are. So we're looking at, it's qualitative, not quantitative, so you can just see it relative to its initial position. And as this maximum point will correspond with when our reference arm length is equal to our sample arm length. Unfortunately, our detected intensity doesn't follow the coherence curve exactly. And so we can use, because the phase difference interference modulates the intensity. So we need to oscillate the laser in some way to try and find the maximum and minimum peaks, and this is sort of how our resolution is limited. So this is the coherence function that we're likely to, similar to a coherence function that we're likely to receive. It's actually a point spread function. So this is for a typical OCT source. But if we use a longer coherence length, it's a lot more dense. So we're looking at relative peaks between these periods. And this is sort of what our detector will actually measure. So by oscillating the mirror, we're looking at the relative peaks and troughs. And so if we oscillate across about 3 peaks, we can say, we're in this position. So our aim is to make this so we have about an accuracy of about 500 micron, like in the previous optical palpation system. And I think it should be around $5,000 to $7,000 to do this. So how am I going to do this? Stage one, we need to find a highly reflective coating so we can stop using these titanium dioxide scatterers. Once we have that, we have our calibrated silicon layer, so we want to test that on an inclusion phantom. And then we want to test that on excised breast tissue. This is something that's done quite often in our lab, so this is not too difficult. We've actually tested on the phantom already, and these are sort of some of the preliminary results that we're getting, and it looks quite good. Next, we want to design the handheld probe, and this is likely to be done over summer. The first prototype we hope to have ready by February. We need to move away from oscillating with a galvanometer and move to a swept light source, because having fewer moving components in a handheld probe makes it more reliable. And then we want to validate that on the same sort of system that we're like in the same way we're doing now, with phantoms and excised breast tissue. Stage 3, once we have a working prototype, after it's gone through the however many iterations it will take, we want to check it in vivo. So we have, it's sometimes difficult to get ethics approval for intraoperative tests, especially with the short time frame of the master's project. So we might also look at in skin lesions, as has been done before. So this was a suture scar. This is the corresponding OCT image, so you can't even see it. But the palpogram, or the palpation image, you could actually see that there was something there. So it does pick up some features which are not visible to some other imaging modalities. So costs. We're looking at, depending on how we actually put this project together, so we're going to need a new laser, like our galvanometer, our scanning mirrors and whatnot for the handheld probe. It's looking between $6,500 and $7,500, but it comes down to the design parameters that we end up choosing. Those costs are going to be covered by the lab or possibly scholarship. Problems that I might have. Any optical system is it's difficult to, our main problems are with alignment, as signal to noise ratio just goes out the door when you haven't got the laser well aligned. We have, because we're hoping to go with in vivo, ethics approval and timeframes becomes a big issue as well. And timeframes in general, just for having however many times you have to redesign prototypes so that they can, the idea is to have market penetration so that hospitals actually take up these things rather than it just being a good idea. All right, and that's all. Thank you.
You talked about calibrating the reflective layer. Is that because of inconsistencies in the layer itself?
So no, the layer is calibrated. So basically we just need to know needed to know the profile of the layer and how it deforms. Yeah. And
to know the profile
and so it's quite the layer is actually used in a couple of other different imaging techniques we've got at the lab. So it's well understood. We have a lot of data to say that this is how it deforms under these conditions, and this is the lateral resolution that you can get from under these conditions.
Yeah, I was trying to picture mechanically how it works with a handheld probe, because the layer actually has to have contact with whatever it is you're imaging, doesn't it?
Yeah.
And so does the user put pressure on?
Or so at the moment, we've only got a benchtop system. In a handheld case, the idea is so it can image really quickly. So if the user the surgeons are just moving around, can detect whether or not there's tumour there in the tissue. In the cavity. And so because it's just relative comparison. So you're looking at the edges where there might not be any pressure or something like that. So you can just have a look and see which parts might be more stiff. Yeah.
I'm just curious about the human ethics. For imaging like the skin lesions
as with any as with any in vivo sort of testing, I assume that there are some ethics approvals that you need to go through, but I think it's a lot easier to get since you're not doing anything invasive, and there's those risks of contamination and whatnot aren't really there for if it's just moles or scars. Yeah.
Where would you get the people for?
Oh, we have actually a good collaboration with the hospitals, with surgeons and in Fiona Stanley as well as here. And so I think we'll have a plethora of people along the way. Yeah.
Thanks. Any other questions?
Cool.
One more question from me. Titanium oxide phantom. So
What was that?
Titanium oxide, the phantom?
Yeah.
Titanium oxide. Are you going to make it at?
We're not. So we're moving away from the titanium oxide. So we have the silicon layer now with just a painted layer. So instead of the titanium oxide, and we do make them in the lab ourselves. Yeah. With the titanium is, but we're not using titanium. It's just silicon now. So.
Any other questions?
As long as you don't lick it, Pedro. As long as you don't lick it.
We have fume hoods anyway if we were putting things together. Yeah.
Any other questions?